Sorry. All right, so we are on chapter. Let me see what is going on here. Some feedback. We are in chapter 4, working on discrete variables, discrete distribution. And we already started with binomial distribution, actually. Okay. Let me just to remember what we did in the last class. It's going to be the way. Let me just share this blackboard. All right. We have a discrete variable. Usually it's a number of something, number of houses, children, boys, for example, houses. And then we have values that could be none, 1, 2, 3, and that matter, okay, depending on. Uh, in cases that we have coins, I have an echo right there. Let's see what is going on here. Number of head. Remember, we should be dealing with an experiment of 2 heads or 3 heads. Let me put 3 coins actually. So we can observe no head, 1 or 2 or 3, maximum 3. And the probability is uh, 0 means something like that. So we have 1 over out 8. What is, remember, any probability for any individual or any simple event is going to be 1 over 8 because it's 1 over 2 to the third is 1 over 8. So the 1 is going to be 3 of them because you have 1 head is, so you have 1 head and 2 tails, and you can have 3 of them, so you got 3 out. And then you got also 2 head and 1 tail, and then is 3 of them also. And that here is only 1 because only 1 case is going to be 3 head. And then that added to 1 over 8, 8 over 8 is equal 1. So that is a probability distribution. That one is a probability distribution because that one is x, the value x, and that one is the probability there. Right? Then is we talk about expected value. Expected value is the summation of the multiplication of the value times the probability. Times the probability. Let me see is in this. Can you hear me? Yeah, still, right? I have an echo. I don't know why this is an echo. Okay. So the expected value in what you need to do is take the value and multiply by the probability. Okay, and 1 over 3a, sorry, plus 2 over 3a multiplied by 3a, plus 3 multiplied by 1a. So that is 0. That one is 3a. Everything is over 8, actually. 6 and 3 is 12 over 8. What is 4 is 3 over 4 is 2. So that here is going to be 1/2 the probability of 3 over 2. So that is the expected value for that table. Remember, that table is a discrete probability distribution. But, and see, I want to do let me see, the variance. What happened with, okay. The variance is equal to summation of x squared probability x minus expected value of x squared. And then and here we have 0 squared is 0, right? 1 squared is 1, and that was 3 over 8, plus 2 squared on 3 over 8, and 3 of a squared over 1 over 8. That take it to this one. Minus 3 over 2 that we have an expected value of square. So here we have 8, 3, plus 4 multiplied by that is 12, plus 9 over 8. That is minus 9 over 4. And we got 15, 24 over 3 over 8 is 3. So it's 3 minus 9 over 4 was 12 minus 9 is 3/4. This is the variance. And then you have to get the standard deviation, get a square root of 3 over 4. What is going to be the square root of 3 over 2? Well, those are critical values for this kind of distribution. Remember, that distribution is a very typical one. Academically speaking, is easy to prove that one is a binomial. It's a binomial because we have first, we got two possible, we got a number of trials, in this case 3. 2, the probability of any trial for any individual is 1/2. For head, we talk about head, this is probability of success, small p actually, and 3, so Q is also 1/2. That independent, and also we have 2 possible results for every trial, success or failure, head or no head, for every independent trial, right? Remember, we need to do 3 trials, 3 3 times to get the outcome. Okay, so that is a binomial. So because it's binomial, I can say when x is binomial, the expected value of x is equal to NP, and the standard deviation of x, standard deviation, I mean the variance of x is NPQ, and the standard deviation is equal to square root NPQ. Because we know that n is equal to 3 and p is equal to half. So we also know that the expected value is equal to 3 that multiply a half is 3 half. This was the one we got it before. The variance is what? Is 3, a half is 3/4. Exactly the thing that we got before. And the standard deviation is square root 3/2. And then you see it's binomial. Okay, because we have all the conditions for binomial. So any experiment where we get a sample, uh, we want to have a binomial if we assuming that the sampling procedure is with replacement. I mean, we can repeat, values. We want to see some other cases of there. Something that you need to learn is how to compute probabilities using binomial table or binomial. A typical problem for binomial is this. Um, some assume, let me just again, or consider that the probability if the success is of p is 0.02. There's a probability for um, success, whatever is the variable. Okay, let's say the variable is a number of defective items. So there's a probability to any item to be defective in any particular trial. And let's assume also that we take a sample of size 50. Size 50. And then you want to know what is the probability that in that particular sample you have none, any defective, zero. Okay, we can compute that probability, of course, using the formula, right? Remember the formula, right? In general, probability is for probability x equal x is equal to combination of p to the x q to the n minus x. Of course, that is the formula there, 50 taken as 0 and 0.02 taken as 0, and the remainder is q is 1 minus p, pop 98, and that is 50 minus 0. So in that case, This is going to be 1 because it's 50 factorial over 50 factorial minus 0 factorial over 0 factorial. That is 1. That is also 1 because it's to the 0. So the probability is going to be 0.98 to the 50. And that is very, very, the probability you get 0 is almost very, very, small one. That means, that's what I mean, is you may expect to have at least 1, okay? 1 does, but 0 is almost impossible. 0.98 to the 50 is going to give you a really a value, kind of, let's see, what kind of value do we have? Let me just get the probability for, okay, that is one way to get the probability, right? Is one way. Other way to get probability is because those numbers, the real numbers are, is the best you can do. We do is use a software or a calculator is to do it. And give me a second just to show now how to do the same problem using a stat disk. Okay, I want to just get a second to get out and get the studies. Now we have the window for let me just get this ready. Echo here. My God. Yeah, that's me. That's one. Okay. Mm-hmm. All right. Let's see if we can compute the probability for the same question that we had before. Let's see what is down here. Application is not working. Okay, it's reconnecting now. All right. Let's see. Well, I know it's not working. Okay. All right. Let's stop sharing. Let me do it again. Sharing application. There we go. Now, here in probabilities, so we got probability distributions, and you look for binomial distribution. And binomial, what we need is n on p. So if we have n equal to 50, n equal to 50, sorry, this is, I have a problem with allergies. And that was 0.02, right? Okay. Now, what's the probability that have none? See what happened when we do the evaluation and the formula here. You got three different um, tables. The one is probability x equal a value, exactly the value. Like probability x equals 0. Here is a probability x less than a value, and there is probability larger than a value. Of course, the probability less than cannot be less than 0 because the value of the variable is the minimum value is 0, and the maximum value of the variable is a 50. You see that in binomial, the table goes to 50. Should be 50 right there. Of course, to have 50 defectives is almost impossible. You don't get it anyway. Okay, it's very, very, very unlikely you have a 50, 50 all 50 being defective. Actually, so you check the distribution, you may have one defective, you may have zero defective, 36% of the cases, 37% of one, 18 two defective, almost 19%, 6% three defective. When you go by four, you got 1%, and less than 1% is, I mean, less than even point 0, in that case, is 0.0020%. 0.20, uh, which is very small one. The probability you got 5 then be defective. Anything else is very unlikely, you see. Good, good unlikely. So the probability that you have more than one defective is 63%. But probability you have 20 more than 2 is 26%. 7% is the probability that you got 3 of them defective. 1.74 and probability that you have 5 defective is point 30. I mean, more than 5. You see, the rule is you have more than 5 effective, the order is going to be canceled. So the probability you have is very, very unlikely that any order could be canceled. I mean, it's very small chance that happens. Okay, that is what we mentioned, like computing probability. You see, we do that whatever we did on this case. So we're using 3 trials, and here is 0.50 using the coins approach. Oh, it's 60 is pasted, and we do the evaluation. Check the table because we have 3 trials, right? Three coins. You have this probability. This is a 1-8. There's 1-8. There's 3-8. 3-8. This is the table, right? And then there's a probability to have 0 heads. Okay, the mean is 1.5 head, the standard deviation 0.86, and the variance is 0.75. Okay, that is why, and that particular software helps us to get all the tables and the way we read this table, right? We read the table. Suppose I want to just play with this one and say, okay, I have 10. Okay, let me just go to 10. Let me get 10. Trials, and that means the probability for is 0.50 still. All right. Do the evaluation, and we got this tables. Okay. Using the 3 tables, we can answer any question about binomials. First, we can have a question like ask you to what is the probability exactly to. So you go here and get this 1. Exactly to. The probability is less than 2. You read here 2. Or what is the probability greater than 2? This one here. Probability that in that case you have more than 1 head is 90%, 99%. You have probability that you have one or more heads. So yeah, that case is that one here, more than 1, greater than equal to 1. Okay. So any quantifier that is given, the table is going to help us to get it. Okay, that's for binomials. And also, we have here probability Poisson. We need to study Poisson. What does that Poisson mean? Um, we know that anything else. So we're going to just review binomial and Poisson. There's a two part. Okay. Okay, let's stop sharing here. And we go to. Okay, so that is for binomials. All right, binomials. Get it? Is that the one? No, it's not the one. Okay, binomial. Okay, the Poisson. Sorry. That's not the correct condition for Poisson. It's also discrete. That means we count the number of times a certain event occurs during a given unit of time on a given area of volume. So anything that deals with time, volume, area, dimension like a distance, weight, or any other kind of measurement, more likely it's going to be a Poisson distribution. Okay, it's a little bit different than binomial. It's discrete, but it's not really binomial. The probability that event occurs is a given unit time, area, volume is the same for all units. It's constant, I mean, it's the same probability. The number of events that occur in one unit of time or area, volume is independent of the number that occur in other units. The mean or expected number of events is in each unit is denoted by Greek letter alpha, or sorry, lambda. You see that is the four condition for Poisson. For example, what is the probability that we have a particular cell and I don't know, very small area in the body, and any drop of blood, for example, that's Poisson matter. The probability distribution is this. That's a way we compute one of x is 0, one of x is 1, one of x is 2. It's discrete, of course. The mean is a lambda. That's the number lambda. But also the variance is lambda. There's only one parameter. That's it. The parameter of this case is mean, and the same thing that the variance. So any question that you have a mean, and is more likely to be a Poisson procedure, Poisson approach. Okay, check the formula here. Is the mean to the x value E is a constant, 2.71828, which is E is a constant, and also to the mean minus the power of the mean, and divided by the factorial of x. That also is a formula that you can work using the calculator. You can use for it's very efficient when we have very small. We can apply for any sample, any mean. I mean, any value mean because it does depend on the sample. Actually, depend on the average. That's why we can use this one. But the reference is what is the probability that a particular number of cars passes through pass through a toll, or that you get a number of cars in the window in fast food, the fast and hamburgers and kind of have restaurant or something like that. Anything that may happen in 1 hour, in half an hour, in a minute is what's on. For example, number of calls that can receive the police in a particular hour. So what is the probability that you have no calls? Or what probability you have more than 10 calls? Or whatever. This is the case that we deal here. Modeling this kind of the probabilities, this one again is given the mean, and then you have you need to compute the probability. The next is, I think, is a table. Okay, and the table is for okay, this is a portion of some table, and actually is given by two positions. That one is lambda 2.2, or is 2.20, 2.21, and on and on and on. And then you have this part. When the lambda is 3, exactly 3, there's 1.05. I mean, this is the probability, actually. Okay, so that table works for that particular number of lambda. Well, the lambda is different. This one, so the table doesn't work. And now we need to use a different approach, a different tool, right? Okay, so that is the two function, the two probability function that we want to have for distribution, for probability distribution in that section for discrete variables. And that's the way we can use for computer probability. Let me see if I can find some files. Let me just go to files here. Yes. This is crazy. All right. For probabilities, uh, let me see what is this one. Yes, could be the one. Let's review this. Okay, let's check this. Oh, oh yes. Excuse me. All right. Can you hear? I mean, can you hear me? Okay. Yes. Problem with this sound. It's not here. Okay. What I need to do is get this. Excuse me. Let me get a file to equals okay, let's see that one. Okay, some examples that we need to check. Assume that the male or female birth are equally likely. That means it has the same probability. In that case, 0.50. And that the birth of any child does not affect the probability of the gender of any other children. Find the probability of exactly 9 boys and 10 births. Okay, they don't tell you anything about what kind of table or what kind of distribution we need to use, but you need to figure it out. Assume, like I mentioned before, is you take a sample, and in the sample, even they don't tell you that is it's kind of sampling procedure, but they tell you that equally likely. See, the probability is equally likely is more I mean, the probability that we have independent sample or replacements sampling is there, like any binomial case. There are independent trials actually, because you want to select 10 different birth, and those are independent, so and the probability is equally likely. It's the same for female or male, so that is basically a binomial probability. And then what you need to do is check the data that's given. The small p is 0.50, and the number of particular uh, success that we're looking for, or birth in this case, is 9. 9 to be boys, of course. So what is that probability? So probability that x equal 9, exactly 9. You need to go and do this on let's see if we can use a studies. We need to share the okay, let me just stop sharing this one. And then we go to share file, share application screen. Window is not there, open anymore. This is something else. We need to get this ready to go. Now maybe it's gonna be there. It's not there. Okay, it's there now. We share, and that is analysis, probability distribution, and then you go to binomial. So 10 and 0.50. Do the evaluation, and that is, what is the probability to have 9 boys? 0.0097 or 0.97. That's not 1% addition that may happen. Okay, so that's clear. What is, how do we use probabilities? Next time I want to be working on probabilities of questions on studies. So we want to review binomial distribution and question about Poisson distributions. Do you have any question? Okay, check your check your website in MATLAB and check it for the homework. Okay, so we almost finished the probability, discrete probabilities now. We want to introduce next time, I want to introduce the continuous probability, which is part of the chapter. This is what 5, 6, 7. So now maybe the half of the chapter is going to be enough to do the second task. All right, and that's going to be before the holidays. Okay. Sorry for the echo, but I have a problem with our audio here. So, all right, guys. If you have any question, I want to let you go, and please keep working. Next time, I want to be working out that section of the problems, and let you you know how to use studies to work out the kind of problem. So go to studies, and there in probability you have binomial or Poisson, and you can work it out all the computations. Other than that, you need to understand the questions. That's all. Ready? Good night. Good night, guys. Thank you for stopping by. I'll see you next class. Have a nice weekend, actually. Thank you.